All right, so if you look at a problem like this, you might go way back in your memory banks to the earliest parts of this course, and you might think that this looks similar to some of the stuff that we did back then. Okay, this is saying find the maximum normal stress carried in this part when it is subjected to this 5,000 pound tensile load acting in the part, right? So we know exactly how to do this. What do we do? Okay, the maximum stress is going to occur wherever you have the smallest cross-sectional area, someone says, which I agree with that. So we would say, if we go all the way back to our very first things that we learned in here, we would say that the normal stress here is going to be equal to what? Okay, force over area. The force is 5,000 pounds. And then you would take that and divide by what? Okay, we need to figure out where is the area the minimum. What's one possibility for where the area is the minimum? Okay, the little part where there's a reduction in the width of it, where it goes from 3 inches down to 2 inches on the right end of it. Okay, so how much cross-sectional area do I have right there? 2 inches times, okay, you see up here we've got the thickness of this part, so 0.5 inches. Okay, and this makes the math work out really nice, so we can mostly talk about the idea, right? So what does this end up predicting as far as the stress that's going to be felt over there in that front tip of this part? Okay, 5,000 pounds per square inch. Easy stuff, right? Well, I don't know if you guys knew this or not, but SolidWorks, which is a piece of software that you guys have become familiar with here, SolidWorks also has the ability to take parts like this and tell you under a particular amount of load how much stress is going to occur in the part. So what I'd like to start with today is to pull up SolidWorks and let's see what SolidWorks says is the worst case stress. Okay? Real quick before I do that, is there another candidate for where the worst case stress could be? At the hole, right? Well, if we look at the hole, so this is kind of on the right end. What if we look at the hole? Okay, there, 5,000 pounds over what? Okay, same thing basically, but you would get to it by taking 3 inches minus 1 inch, because basically you take the total width and subtract off the material that's missing because of the hole, and you take that and you multiply it by 1/2 an inch. Okay, so I also did that on purpose to where they wind up being about the same. Okay? So, but like I was saying, SolidWorks has the ability to tell us how much stress is felt in a part. And so let's take a look at SolidWorks and see what it says the stress might be in a part like this. Okay? So I'm going to go into SolidWorks here, and I'm going to go into File, New, and we're going to start a new part. Some of you might be using a more recent version of SolidWorks than me. I apologize for that if it throws anybody off, but this is still what I've got on my computer, and it hasn't changed that much. All right, so the first thing you want to do once you've started a part here is we want to actually draw the part, right? We haven't drawn it yet, so we need to go in here and draw the part that we're talking about. So to do that, let me start a sketch. I'm going to put this sketch on the front plane, and let me kind of just start by roughly drawing something that is about what I want. Something like this. Okay. Now, when you do this, there's a little bit of care you need to take because it's going to apply a lot of relations as I'm clicking through. It's going to apply a bunch of relations. As I put this little shape together, I was doing it rather quickly, but I was trying to keep it from adding too many relations. Right now, all I really want is horizontal or vertical relations for all of these things. So now what I'm going to do is take this point right here and this point right here. I'm going to say merge those points, and it makes this, you know, funky looking shape here. What else do you think I might be able to do to sort of make this the proper shape? Okay, I'll tell you what, let me put the hole in the middle of it too. Okay, tell you what, I'm going to actually put the hole such that the hole is centered on the origin. This doesn't matter that much, but we'll just go ahead and assume that that's what I've got there. And the hole was how big? Okay, 1 inch, so I'll go ahead and dimension that. Okay, and then it was between this edge and this edge down here. How far was it? 3 inches. Okay, between this edge and this edge was 2 inches. Okay, one of the things I can do to make sure this is centered, I can apply a relation here, and I can say, let me get out of my dimensioning tool here. I want to make this little segment right here the same length as this segment right here. Okay, so I'm going to make these two things equal to each other. That'll sort of center up this thing. Now let me do this. I want to make this piece right here collinear with that piece as well. Right, so that'll kind of make the shape do more like what I want it to. Let me show you another trick you can do. You can add center lines, right? So if I draw a center line from corner to corner like this, one of the things that allows me to do is that center line is not going to be part of whatever part is created. It's just there to help me draw things. So I can take that and choose the midpoint. Okay. Choose the midpoint, select midpoint, right? And if I want, I can make that, if I select those two things at the same time, I can make those two things coincident with each other, which is going to kind of center that hole in this part. Okay? Now what else do I need to do to sort of, you know, fix the rest of my dimensions that might matter? Did I have this dimension down here? Okay, we can flip back over here and look at it, but what was that dimension? Okay, 4 inches. Okay, and then this dimension right here probably needs to also be specified, 2 inches. All right, so now I've got my shape that's fully defined here, and I'm going to turn that into a feature by doing an extruded boss base, right? That's what SolidWorks uses to create this actual shape. And some of you might be wondering, on the original that I had fillets. I had like little curvy things on these interior corners, all right? I left those off at this stage on purpose because one of the things I'm going to play with after a little bit is changing the values of those, and it's easier to do that if you use an actual fillet feature at those locations instead of drawing it into the figure. So anyway, just to explain why I'm doing what I'm doing there. Okay, we're going to make this 1/2 inch thick, right? And then I'm going to just do this as a mid-plane. Now, this doesn't really matter very much, but that basically makes it to where the origin is going to be centered in the middle of that hole. Okay, so there I've made the basic shape of the piece, and what I want to do now is add the fillets. So I want to fillet on this little edge right here, okay? But I'm going to also select another edge, right? And it's kind of cool. Sometimes if you just hover in the right spot, it'll let you pick an edge that's not necessarily the thing you see when you look at the figure and the orientation it's in right here in this, you know, at this moment. So anyway, I'm going to pick that as well. So those two edges I'm going to fillet, and then I believe we had those set at 1/2 inch right here, right? So go ahead and set these at 1/2 inch. Okay, when I hit check, it has now made the part that I'm going to try to model using the simulation tools of SolidWorks. Okay, so that part should all be review. Just making that part in the first place should be old hat for everybody at this point. Let's start the new stuff. Okay, I'm going to show you that on my instance of SolidWorks here, I have this tab up here that says simulation. Okay, many of you, if you're looking at SolidWorks right now, you might not have that tab in your version of SolidWorks yet. If you don't, it's not that big a deal. You can go up into Tools, and under Tools, there's a thing down here that says Add-ins, and under Add-ins, you can enable SolidWorks simulation. All right, and we have a license for that here at our site. So you can do these simulation things under here. So, and if you don't have the option to do that, it could be that whenever it was installed on your machine, maybe someone didn't take the effort to actually make sure it was that part of it was installed on your machine. You might need to go back and have someone at our, in one of our offices here, look at how to get that installed on your computer, if that's something you're interested in doing. Okay, so this is the simulation tab, and the first thing you want to do under the simulation tab is go up here to Study Advisor. Okay, and under Study Advisor, what we're going to do is go to New Study. Okay, over on the left side, it gives you a few options for what kind of study you're about to do, right? And we're going to do a static study. So it's the very first option up there at the top of the list. Now it has populated the upper bar up there with a number of things that we're going to need to do this study. So the first one that they have there is Apply Material. All right, and it gives you a big old library of certain kinds of material. I didn't tell you what kind of material this was on the very first page. So what do you think we should pick here? All right, you might want to pick a structural steel or something. Let me say this, it doesn't really matter as long as you don't have to answer any questions about how much it deforms, right? That's why it needs to know what kind of material it is that it would need to know the elastic modulus of the material to know how much it would start deforming under this load. And the thing is, internally, the system that it's using to solve for this needs to simultaneously evaluate how much the thing deforms along with how much force, stresses, I should say, it has in the various pieces of it. So anyway, all that to say, it doesn't really matter, but if you want to pick something that's roughly a structural steel, this ASTM A36, that's basically the structural steel. It's a very similar kind of steel to what our structural steel is in the data tables that we've been using in the class. So we'll pick that one. Okay, hit apply and then close. I like how it changes the color just slightly. It says, hey, I've made that, that steel material. All right, next thing you need to do is define a portion of the body that's not going to be allowed to move. Okay, in SolidWorks they call that a fixture, right? And the way I recommend that we look at this is, why don't we fix the left end, and then we can apply loads to the right end, and that'll do the same thing as our original picture, even though up here I wrote it as a 5,000 to the left on the left side and a 5,000 to the right on the right side. It's not going to be much different for us to go ahead and put a fixture on the left end and apply the load on the right end. Okay, so I'm going to do that here. Under Fixtures Advisor, right, I'm going to insert a fixed geometry. Okay, and I want to apply that not to this face right here, but I want to, and I don't want it on the edge either. I want it on the face back there that right now I can't see. So a lot of you are familiar with being able to rotate using the arrow keys on a keyboard. You could certainly rotate that around and pick that face on the back side. But let me show you another thing in case you haven't seen it before. If you right click on here, almost always it will give you Select Other as one of the options in this menu. What that does is it allows you to select things that may not be on the, the side that you want to actually work on, right? The side that's closest to you. So notice there, you know, I can kind of pick that face that's back there and choose that as my fixed face. See that? Anyway, maybe you've seen that before, but some people haven't, and they like to see those nice tricks like that. Okay, so there's a fixed face back there. The next one in the line up here is external loads. So let me go under there, and I'm going to apply a force. Okay. Over here in the little bar, it says, you know, this right here would be faces on which to apply this force. So I'm going to apply this force on this face. And you might notice there that the arrows look like they're applying a compressive force. Is that what we have? It's not. So what we're going to do is a couple things. It's ready to give me these SI units. I don't want to use SI units because I defined my original problem in US units. So let me change that to US. And then under the force, I'm going to go ahead and put in the amount of force that I'm applying on that face. Right, 5,000 pounds. And I can reverse the direction. Right? So there's that force I'm putting on that face. I'll hit check. Okay. We're going to skip Connections Advisor, even though that's a really cool it's got a lot of cool tools in that Connections Advisor because it allows you to figure out how multiple parts will interface with other parts. Like you can do things like no penetration. Like you can have one part and another part, and you can tell them not to penetrate one another, and it'll calculate those contacts between different parts. But anyway, we don't need to do that for this problem, so I'm going to skip that. And the next one on the list is run. And there's actually a few options underneath run. And I'm not going to choose any of them just yet because I'm going to make a strong point here. If you're doing one of these simulations like this, make sure at this stage you save. All right? Because it might actually start trying to calculate this for you. And it very well might crash your computer. And when it does, you will have lost everything that you were just working on. Right? So we're going to save right now. Okay, save. And let me go in. I'll do a new file folder here. Okay. And I don't really care what I call it, but let's say just demo or something like that. So now I've got it saved. And I'm going to, even though you don't have to do this, I'm going to show you multiple steps under this run because I think it's going to be instructive to help us know kind of what SolidWorks is doing under the hood just a little bit. Okay? Under here, you might notice there's an option that says Create Mesh. So I'm going to hit that. What meshing does is it takes the body as has been defined and it splits it up into little bitty pieces. Right? They're called elements. So it splits it up into these itty bitty little elements, and it will basically define that whole piece of geometry that I've set up there as a chain of all these little elements. So let me actually show you this. It gives you a little slider bar to make it either coarser or dense or finer. Okay, so what do you think it means to make that mesh finer? Smaller elements and more of them. Okay, what do you think that does to the solution? It'll take longer to do, but it will probably be more accurate, and it will certainly be better at figuring out gradients of stress and stuff, right? So if there are fast changing values along the geometry, you need to have a larger number of these elements to be able to capture that, right? So anyway, let me slide this kind of more to the fine end a little bit here, and go ahead and hit check. Now I'll tell you that it's not uncommon for SolidWorks to experience some difficulties during a mesh. All right, but this time it actually made it just fine. Yeah. How coarse does it go? That's a good question. Let's play with it. Right. So create mesh. You want me to go all the way? I don't know why it's hopping over to this other thing, but you can see there, it can go pretty coarse. You know, those members or those little pieces now are these, they're actually kind of little tetrahedrons, right? That this thing is all made up of all these little tetrahedrons because that's a relatively simple shape to be able to model how stress propagates through a little tetrahedron. And by stacking all of them up, you can figure out how stress propagates through the whole thing. But anyway, that's the coarsest end of the scale. And we could run it like that, but let me go back to something a little bit more fine here. All right. So there's the mesh. And what do you think you do after that?
Save again.
You could save again. It's not that hard to make a mesh, you know. So I don't think I'm going to hit save again, but let's go ahead and hit run. Okay. Now sometimes that ran relatively quickly, right? And what it has now done is figured out what this thing is going to do. It's showing you an exaggeration of the deformation that part would experience under that load that I just put on there. This isn't the actual amount of deformation it does, but it takes all of the little deformations and sort of, you know, magnifies them so that you can see basically what shape the thing takes on. Okay? But that's not necessarily what I want to see. Over here on the left, it has automatically come up with a few results for me to look at, right? So if I want to see stress, I can right-click on here and hit Show, right? And what it's showing me there is with this scale, this color scale that I have over there on the right, it's showing me how much stress exists in various parts of the piece, like various zones of the piece, okay? So I don't particularly like the units that it just gave me there. So I'll tell you what, I'm going to go in here and right-click on stress 1 here and go to Edit Definition. And under here it says newtons per square meter. I'm going to change that to PSI. Okay? A lot of you might be wondering about what is this von Mises stress. Okay? We won't be able to get entirely into that, but I will go ahead and give you at least a little bit of it. You might remember when we talked about pressure vessels that when you have multi-axial states of stress, there's another step you have to do to apply some sort of a failure criteria and figure out what's going to actually fail the material, take into account multiple directions of stress at the same time. Okay? One of the ways of doing that involves finding this von Mises stress, which you can kind of think of that as an equivalent stress that you can compare to a tensile test value, right? And it's one number that you can compare to a tensile test value, and it's valid to sort of know whether or not you're close to breaking the material, okay? It's based on, in case you want a little bit of terminology, it's based on a failure criteria called the distortion energy criteria, all right? But we'll save that for a future time together. All right, so this is what the stress is. Let me change it to PSI here. Right? So what's my maximum stress according to SolidWorks? I know this is kind of small text up here. Okay, 1.221 times 10 to the 4th PSI. And it says, where does it occur? Yeah, right inside of this circle right here, right? Okay, so this is kind of interesting. This isn't what we would have predicted using our formulas that we've already used, force over area. What's going on? Okay, so the materials that have discontinuities in them. Discontinuities can be things like a sudden change in cross-section. Right? A hole is a sudden change in cross-section, right? Over there, you might notice where the thing has actually reduced in size, right? These little areas right over here, it's reduced in size. What do you know? Why does it have this little yellow spot right here? Okay, that's another spot where it has actually started to concentrate stress at that location because there was a change in geometry. All right, there's a change in what the cross-section looked like. And this happens for a lot of different kinds of changes in geometry of a part. If you suddenly go from one size to another, then it a lot of times will concentrate stress at that location where you've changed from one thing to another, and it will actually have more stress at those locations than you would have predicted even after having accounted for the missing material because of the hole, which we already did that, right? But there's even more than that just because there's a discontinuity in sort of the fabric of the part. Okay? So that's kind of interesting. What do you think might affect that, this stress value? Okay? He says the radius of what? The radius of the fillet. All right? Let's play with that a little bit. Let's go back into the part, right? This fillet right here, let's change that definition. Okay? Let me change this to, where is it? There it is, right up there. I'm going to change it to, instead of 0.5, let me make it 0.1. Okay? Once I've done that, the part won't necessarily update right away, and it's going to need me to remesh the part, right? Because I've changed what the geometry was that the part is made up, so it needs to actually redo that mesh step. So let me go up in here and hit mesh again. Okay. I'll leave it with the same, relative level of density, but you'll notice here that now we've got this much tighter radius right here. Okay, so it meshes, and then we'll go ahead and solve it. All right. So go back into stress here and show that piece. Look what's going on in there now. We've got some pretty strong, red spots. Let me ask you this. Do you trust the kind of the shading of these red spots right here? Is there a reason in your mind why we should have a really strong red zone right here that doesn't even necessarily look like it's symmetric with the other side? Does that seem like that makes sense? Okay, so he says that's due to the mesh, right? This means that I probably don't have a fine enough mesh to actually capture the changes in stress that happen right there at that zone. So what should I do about it? Might want to make a finer mesh. And this is always, I always feel like I'm playing chicken here a little bit, because I usually find that if I take this thing all the way to the fine end, I'm much more likely that something's going to crash when I try to mesh it. You guys feel lucky? What you got?
What is this calculation that's calculating these forces based off the resolution of your mesh? What component of your computer is it depending on? Is it like your GPU?
Okay, his question is, what exactly is the limiting factor in terms of the computational power of your computer in order to be able to do these calculations? Let me kind of describe this for you a little bit. So each one of these little elements that it makes, let me go ahead and hit mesh and we'll see how this goes. All right, looks like we made it. So each one of these little elements that it creates right here, each one of them has to be in equilibrium. Each one of them has relationships that are applied to it that predict how much it deforms, right? And each one of them interacts with all the other ones around it, right? So there are all these relationships that are set up per element, right? How much does it deform? Whether or not it's in equilibrium, how does it interact with all the pieces that are around it? And the result is a really large system of equations. Like, look at the number of elements, and there's multiple equations per element, right? And it has to solve that giant system of equations in order to figure out all those forces. That involves a lot of things, but one of the big things it involves is you need a good bit of RAM. Like, it needs to be able to store a lot of the data that it's actually operating on as it does that process. You know, obviously having a good processor to be able to do the floating point calculations and all that stuff, that's good too. So it's not necessarily my exact area of expertise, but there, you know, it's almost not much of anything that it doesn't rely on in order to do a calculation like that.
I just want to know, like, the limit, like for your computer right there, do you know it's how much?
This computer has 16 gigs of RAM, and it's about, I think it's a 3 gigahertz processor. Okay. All right. So shall we run this? And we'll see what happens. Okay. While it's doing this, this is one of the longest ones probably that it's going to take to run. You can actually force it to show you. I ran out of time there. There's a thing that you can actually see how the solution's converging if you're doing a problem that's like really heavy. All right. All right. So we're still looking at this same little spot, and let's show what the results are. It looks like we might still have a little bit of stuff going on because of the mesh, but it's a lot better than it was, right? Did it change the value? A little bit, right? A little bit more than nothing, right? So anyway, we're at 1.518 times 10 to the fourth PSI at that location. Is it worse here than at the hole? Yeah, what changed?
The radius of the fillet.
Yeah, that fillet radius made a big difference. It's a strong function of just how much of a radius you have right there. Yeah.
So when we had it before, the radius was 0.5. The radius of the circle in the middle was also 0.5.
Yep.
Why were they not identical?
Why? Okay, so his question is, the first iteration of this that I ran, they both had the same radius, and yet one of them, the hole, looked like it was a worse case than the reduction. All right? I'll say it's that way because it is that way, right? But you know, we will, because they aren't the same, right? It's different situations, so we shouldn't necessarily have an expectation that it would end up being the same. But I'll show you a little bit of maybe a secondary confirmation that maybe we're not too far off. Okay? So let's go ahead and grab that value, 1.518 times 10 to the fourth, okay, PSI. And we'll say this is the results from our finite element analysis. Okay, and actually, this really wasn't our result for this exact problem, was it? Okay, this was the result when fillet radius was what? Okay, 0.1. Okay, shall we go back? I should have written it down when we were there, but shall we go back and change this again so that we figure it out for our original case? Okay, go back in here, change this back to 0.5. Okay, remesh. And then run the study. Okay. It goes pretty quick. If you're working on a harder problem, you can kind of see how the various variables converge. All right. So we'll show this, and now our worst case scenario happens at the hole, right? So we'll look at these two cases. This one for the hole, what's that maximum value? 1.221 times 10 to the fourth. That's the same as it was before, wasn't it? So our changing of the mesh size, because we changed the mesh size a little bit from the first time we ran it to what we did just now, didn't have much of an effect on what that value was. That's actually a pretty good indicator that our mesh was probably fine enough for that question before I changed it again. So anyway, so let's write that down. 1.221 times 10 to the fourth. Okay, so this is for the reduction. And then we had another one, 1.221 times 10 to the fourth PSI. Okay, and this is for the whole. So what I was about to show you is this. People needed to be able to do these calculations before finite element software was readily available, right? People have been designing mechanical parts for a lot longer than a tool like SolidWorks or something like it were available to be able to find whatever these stress concentrations were through this finite element method. So how did people do it before? Okay, there's a couple ways. These things are based on some interesting equations that you can actually come up with manual solutions for, right? They're not easy to come up with, and sometimes they're not even possible to come up with. Other times, people have done studies that might be called photoelastic studies. So there's a way that you can coat a piece of material with a particular coating and then pull on it and look at it with a polarized light, and you can actually see the part. You can see the various stresses that act in the part by looking at these changes in color bands that go across the part. There's some pretty neat things people have figured out how to do in order to figure out what these stress concentrations are before you could really reliably use computers like this. And based on all the results of that, the results have been put together into certain charts. And I know this one's on its side here, but this is the reference material that you have available for you to use. That's one of them right there. Okay? This is a case where you've got a hole in the middle of a plate. This is a case where you've got a reduction in the cross-sectional area. Those are basically our two cases that we're dealing with right here. What do you think K might be? All right, let me show you. For all of these, if you wanted to do these by hand, they're all based on this idea that our actual maximum stress, once you've considered stress concentrations, is going to be whatever we said the stress was before, which now we're going to call that a nominal stress, right? That's what we would have said the stress was before we knew anything about stress concentrations, multiplied by this K factor, and that K factor is called a stress concentration factor. It's just, you just multiply by it, and it tells you what the actual max is as opposed to what you would have predicted before you knew anything about the stress concentration effect. Okay? So if we can figure out those K values, then we should be good to be able to calculate what these maximum stresses are. And the K values can be found off of these charts. So for our problem, what do we need to do? Let's look at the whole first, okay? And let's orient ourselves with what it's giving us on this picture. Along the bottom, down here at the bottom, what is this? Ratio of radius versus diameter. How do you know what it means? Okay, I know this didn't actually pop very well on the colors here, so let me put this on here. This is saying that the radius of this hole is r. Okay? What's d? Okay, you might be able to see these a little bit better. It says you've got 1/2 d available on each side of the hole. Okay, so d is the total amount of material that's left over there. All right, so for our problem that we have up here, r is 1/2 inch, and d is what? 2 inches, because we've got 3 inches minus 1 inch. Okay, So we're dealing with R over D of half over 2, right, which is 0.25. What do I do with that? Find it on here. That'd be this location right here, right? Maybe I'll do that in a little different color so we can see it a little bit better. Find this point on the curve and read across to here. Do your best shot at reading what that value actually is. Keep in mind this is like 2.4, 2.6, so in the middle would be 2.5. So what's our best guess as to what that K value might be, just reading it off of this chart? Okay. 2.43 sounds good to me, right? The 2.4, you're very confident of that. The next digit, you're going to make your best guess, right? Just by looking at the chart. Okay, so 2.43, and so that's K. And so for our problem up here, what is now our maximum stress we would predict at the hole? Okay, maybe I'll put that right here. Okay, all we're going to do is take that K factor of 2.43 and multiply it by what we just calculated a second ago, right? 5,000 pounds over 3 inches minus 1 inch times 0.5 inches, right? All of that stuff, all the stuff in the red brackets right here is the nominal stress, and I'm multiplying it by my stress concentration factor in order to come up with what this actual maximum is, right? So 2.43 times 5,000, we already calculated that, 12,150. Does that look relatively close to what we came up with using SolidWorks? We came up with, this here is the same thing as 12,210 psi. Those are pretty close, right? What SolidWorks said versus what this chart said, that stress is going to be at that hole. Okay, shall we do the other one? The other one's just a little bit, there's a little bit more trickiness to it because there's instead of just one curve, there's a set of curves, right? So I can go down here, and now instead of finding R over D only, which by the way, let's do this for the, once I reduced that fillet down to 0.1. So in other words, I'm now working on this where instead of this being 0.5, this is now 0.1. Okay. So R over D is going to be what? 0.1 inch over, what's D? 2 inches. It's the width of the narrower part. Okay. This will be what? 0.05. Well, what else do I need to know? D over D. Right? These are all these different curves are different capital D over lowercase d. What's capital D? Okay, it's that larger width of the two parts. So for us, capital D is what? 3 inches. Lowercase d is 2 inches. Right? So 3 over 2 is equal to 1.5, right? So that means we're not on that curve, we're actually on this curve, right? Pointing at that curve right there. So how do we use this? Well, we grab our R over D value of 0.05. It's going to be right in here somewhere. We read up, okay, to the point where we hit that curve. 1.5. Once I hit that curve, I read across to here. Keep in mind, halfway up right here was 2.5. Okay, so you like the idea of 2.7? Looks reasonable enough to me. Excuse me, you're right, 2.7 was that middle spot. Excuse me, I see what you were saying now. This point that I drew right here was 2.7. And so this point that I'm picking off now is what, you think? Okay, 2.72 or something like that maybe. Okay, so 2.72. will be that K, 2.72 times 5,000 PSI. So what does that give us? $13,600. Okay, we wound up a little bit further off on that one, right? Not necessarily a huge problem, but it's, you know, two different ways of coming at it, and you know, it could be a couple of errors in there, right? It could be that maybe SolidWorks, maybe we still needed a more fine mesh in SolidWorks. Maybe we didn't have that mesh fine enough where we really figure out what the actual max is. Maybe we didn't do a real good job of reading exactly what that stress value was off of this chart, right? Like maybe I should have not had 2.72, maybe I should have 2.73 or 2.74, right? It's not necessarily easy to read off of this chart exactly what that should be. So my point with this is this. Using these charts gets you to some level of precision. It's not perfect, right? You're not going to be able to go out to 16 digits and get exactly the same result as someone else, right? But it gives you a really good idea as to how much stress, you know, is actually being experienced in the part once you've accounted for these stress concentration factors. All right? Questions yet? Okay. Yeah, go ahead.
How wide are the margins on the exam?
Okay, he wants to know for the exam just how wide are these margins. I'll show you a couple of different things that we could do. What if I had solved this problem and instead of telling you that the radius of that curve right there was 0.12 instead of 0.1? Everything else is the same. I make the radius of curvature for the fillet 0.12 instead of 0.1. Okay, what that would do is it would shift over to where R over D would calculate to now 0.06 instead of 0.05. So then I could read up this line up to where I hit this curve, and holy moly, that gives you a really solid value of 2.6. That's one of the things that we commonly do on exams to make sure, I mean, we don't always do this, but this is something that is commonly done so that people have a little bit more of a good feeling about it when they've done it right. They can be pretty sure that's probably the number we were shooting for K, okay, as long as you did it right. Now, another thing that we can do there is we'll a lot of times give you results that are only a couple of digits of precision, right? We'll say, is it 2,500 PSI, or is it 2,700 PSI, or is it 2,900 PSI, right? We'll make those more broad so that you can feel like, yeah, I think I've maybe got that right.
That's what I was getting at, because this one we were almost 2,000 PSI off.
Right. Although we were that much off. He says, for this one, we were almost 2,000 PSI off. That seems like a lot, right? And I would say it does seem kind of like a lot, but it's not 2,000 psi difference between one person reading the chart and another person reading the same chart, right? It's 2,000 psi difference between a totally other method, finite element method, where we're not even sure what sorts of, we're not super sure for that one what sorts of error we might be introducing because of the nature of that method being an approximation anyway, right? So anyway, all that to say, you're going to be closer than that, being that it's two people trying to read the same chart and answer the question on an exam. Yeah.
I have a question about this SolidWorks simulation.
Yeah.
How would we apply a load, a directed load on the inside of like a pin hole, as if we were going to do it for like a truss member?
Okay. He says, what if you wanted to apply on a SolidWorks simulation, you wanted to apply a load to the inside of a hole? Okay? If you want to know what probably the most realistic way to do it is, it's to go ahead and also model the pin, okay? And then put the pin in the hole, right? And then specify no penetration, right? What that does is SolidWorks will say, all right, SolidWorks will say, I've been instructed to not allow the pin to move through the material that it is now inserted into. So once it detects that there's going to be contact between the pin and the hole, it will say, I'm not going to let it go through the hole, and I'm going to calculate how much force exists on that surface where the two parts contact each other. So that's probably the most realistic way to do it. Short of that, the other thing that you can do is you can apply a fixture to that hole, right? Like instead of applying the fixture over here on the left end, a quick and dirty way to do this would be to apply the fixture just on that hole and then apply a load to that. Now, that's not exactly right, because in real life, only half of the hole is going to be interfacing with the pin, because the pin is either going to be pushing to one side of the hole or to the other side of the hole. But it's a way that you can at least get somewhat close, maybe. Yeah. All right, so you want to know, could you put the whole thing together and then load it and see what it would do? If you're trying to model a truss in this thing, okay? There's a few reasons why that becomes difficult, okay? So one of them is you end up needing a fairly fine level of detail at the holes in order to actually be able to resolve the kinds of forces and stresses that occur at the hole. And if you use that level of detail across the whole truss, you end up with a lot of elements, like an insane amount of elements. So there are some tricky things you can do to make it have a tighter mesh in the locations where you need a tighter mesh, and to go to a coarser mesh in locations where you don't need the tighter mesh. It's a little bit outside the scope of what I was planning on teaching you today. Okay? So someday maybe you will be able to use this to do an evaluation of a larger structure. That's not necessarily what my goal is for you. This is mostly, I wanted to at least introduce the idea that you can calculate some stresses in SolidWorks. It'll show you about insights that have to do with the stresses that might occur in members that might not have occurred to you unless you had this to show you, right? We might not have known about stress concentrations unless we had done some sort of an experiment with this, and it starts showing us, hey, it concentrated that stress a lot in these particular locations. Maybe we should do something about that. You know what I'm saying? So there's a couple of goals that I had with today, but it's mostly an intro, right? Just there's this tool available. The nice thing about SolidWorks is it's very easy to learn, believe it or not. It's one of the easiest ones of these packages to learn, in my opinion. And so if you want to play with it, I highly encourage you to start messing around and see what you can make it do. The other factor that would happen with one of these wooden trusses that we're building, that this method is not even going to be able to do it without we'd have to actually introduce a whole other sort of set of tools that SolidWorks had if we wanted to be able to do this. But this is not going to evaluate buckling. Right? That's a whole other kind of analysis that it's not doing in this setup. Okay, so it'll find stresses, but it won't evaluate whether or not something is buckling using our technique that we just used right here. Buckling is another module that's in here, but again, it's more effort to learn how to use. Not saying you can't learn it. I'm just saying it's a little more effort to go in there and figure out how to use it. All right, one last comment and then I'll let you go. Okay. What if this is a structural steel, an A36 structural steel, which means it has a yielding strength of about 36 KSI. And what is the ultimate strength approximately of a structural steel? Does anyone remember? Okay. 66 KSI. We can look that up if you want, but in our reference material here, up here at the top, okay, we have 36 KSI for structural steel and 66 for your ultimate strength. What that means is you have a lot of deformation that this material can do before it reaches the amount of stress that it takes to actually break it. This is what's called a ductile material. Structural steel is a very ductile material. It means you can bend it and stretch it quite a bit before it actually will start to, want to crack. Okay? So if you have that in mind and you go back to our problem that we're trying to solve here, and actually let me go to the SolidWorks thing. Where's the only material that's reaching these high stresses? Yeah, like not very much of this material is reaching those super high stresses. And what if you go out here? Like it's hard to see it here, but it says out here, you're at more like 4 KSI out here. Right, or maybe, like 2 KSI or so out here. Okay? So what do you think I'm getting at with this? So where I'm going with this is this. It's not always the end of the world if your material yields a little bit locally at one little spot. Right? We're not saying it broke. We're saying it deformed permanently once it reaches those high levels of stress. So think about what would happen on this if you reached high levels of stress enough to deform it permanently right here in this little zone. So then it deforms permanently. What happens then? Okay, so what it'll do, it'll move stress away from that zone and force the other material that's still here in this cross section, right? It'll force that material to carry more stress as it yields a little bit, and that transfers the stress outward into the material that's not currently holding a lot of stress, right? And so here's the principle we can draw from this. There's a lot of times where when people design with ductile materials, they ignore stress concentrations. And this is exactly why, right? If you're designing with ductile materials, you sometimes, as a matter of fact, very often you don't care what this maximum stress is as long as it's super localized, because your presumption is once I put it in service, it's going to yield a little tiny bit right there, and that will equalize the stresses across all the material that's there available to hold the load, and I don't really care if it yields a little bit locally right there in one spot. Okay? I know that's a little bit hard to think about, but there's, one of the reasons I tell you this is I'm trying to actually give you a little more confidence again in our earlier calculations we did in the quarter. Because we did things like, hey, how much force can it hold before it breaks? Right? And, now that you're applying this kind of thinking to it, thinking, I wonder if we considered stress concentrations on all those problems that we did earlier in the quarter. What I'm going to tell you is, if they're made out of ductile materials, there's a pretty good chance that it wouldn't matter anyway. Because the presumption would be that the material would yield a little bit, and then that would just transfer load that had been concentrated all at one little spot into more of the material, and you're fine. Okay? And that was about all I wanted to say. Any other questions? Yes, sir.
What about the other forms of, like the shape up there where you have the bolt-looking one and the one with the two divots?
Okay, so you might be saying, what about these other ones that are here in the reference material? So let's kind of scroll through here. So these are the ones we looked at just now. Okay. Are there any other ones? Here's another one. What's this one? Oop. Okay. It's the same geometry as what we just calculated, but instead of carrying an axial force, what's this one carrying? A bending moment, a flexural influence that's happening on it. Okay? And it has its own set of curves for dealing with that flexural version. Okay, there's another one down here somewhere, right here. This one is for torsion. So if you have a shaft that reduces in diameter and you're twisting it, right? How do you know that this one is torsion versus the other one that's a bending moment?
Because it shows you the forces applied.
Okay, this one's pretty obvious. It's showing you that you got these two bending moments that are being applied to it. This one's a little bit less obvious because they didn't do a real good job on this one of labeling the torque. So for this one, let me just go ahead and make that clear. Say this one's for torque. And if you want a little clue, other than, you know, me telling you that, they did show you that it's a roundish shape by kind of how they drew it, right? It does give you the idea that this shape is circular. But anyway, I know that may not be, you know, enough or totally desirable, but let me just go ahead and say this entry that we've got here is for torsion. And this will allow you to calculate what these stress concentration factors are for that. Okay, here's another one. What's this one? Whoop, come on. What's that one there? Okay, it's another flexural one, but what's the difference on this one? It's basically got two little notches cut in it, right? So it's a little bit different than the last one, the last flexural one that we looked at. This is also, let me say this, these charts that we have in your reference material that you'll be able to use on an exam or whatever, these are by no means exhaustive, right? There's actually books and books that people have put together of charts like this for various kinds of cases. We just picked a few of them that might look interesting, make it easier for us to write a particular problem. And we threw those in the reference material. But once you know generally how to read one of the charts, the process is the same regardless of what kind of geometry you're looking at. Okay. We good? All right, let's call it a day.